Hello, everyone. I'm very delighted to introduce our next speaker, who is one of our Mars alum, Jason Dunn.
My favorite selfie. Hi, my name's Jason Dunn. I'm the CEO of Outpost, the company that's making satellites that return to Earth. And Outpost is really my love letter to the space industry. It's a company I always wished existed. I'm really pleased to get to share the story about it here today. This is really the first time in the 2 years of building the company that I've got on a stage and told the story. So I feel honored that it could be here at Mars. Before I get into that, I'll tell you a little bit of a backstory about myself. I had a really unique childhood where from an early age I fell in love with the natural world and became obsessed with protecting it. I grew up on the Gulf Coast of Florida on a direct line across the state from Cape Canaveral. And my days were spent exploring the grass flats and mangrove islands on my little 12-foot aluminum flat-bottom boat. And on a really special night when a space shuttle was launching, I could go out into my front yard, look to the east, and see that little star rising up to join all the others. And it wasn't lost on me, even at that young age, that while I was having fun tinkering around in the ocean on my little boat, that these astronauts were probably feeling a similar joy as they left the shore of Earth to explore the coastal ocean of low Earth orbit. And it was these days that made me become fascinated with how space and Earth are very much connected. And it set me on a path of seeing how space could one day be a solution to protecting our planet. Now, fast forward to today, and that dream is still keeping me awake. Today, I'm going to share with you some of the work that I've been doing with Outpost to continue on my mission of really finding ways to make space a gateway for a more resilient Earth. The story of Outpost is really the story of friendship. It starts with one of my best friends, Mike Vergala, and I coming together to build the company. Mike is a world-class paraglider who also happens to be a world-class engineer. And he shares this vision of making Earth a sustainable home forever. So we came together, and what we ended up doing was formulating a very new way of doing satellite missions. In case you're wondering, Mike's the guy on the right. The one in the middle is Buzz Aldrin. This was back when we were building lunar landers together, and Buzz came out to check on the work. Okay, to set the stage for Outpost, this is the reality of where we're sitting today. Every year during the dry season, the entire west coast of the United States experiences destructive wildfires that devastate communities, destroy huge areas of land. In 2019, the Kincaid fire here in California was one of the largest and most destructive wildfires in state history. In fact, it burned over 77,000 acres of land, destroyed hundreds of homes, and displaced thousands of people. Now, fortunately, we have satellites in space that allow us and first responders to monitor our planet, monitor things like the Kincaid fire here, and make decisions and make real actions, and not just for fires, but for all the different things that are changing about our planet. This is a photo taken by NOAA of the Kincaid fire. I want you to notice how far away that image is taking. You can almost see the entire state of California. But something's changing in the world of satellites. Now we're flying large fleets of small satellites in constellations. And in a sense, we're really building an exoskeleton around our planet. An exoskeleton that is allowing us to better monitor the change in our planet and understand the changes we're making and be able to make better decisions. To see that on a graph, the number of satellites going to space has gone exponential. Since 2018, more satellites have activated in space in the entire history of launching satellites before that. And the reason is simple. Access to space has dropped over 100x since the space shuttle started flying in the 80s. And that's thanks primarily to reusable mid-sized rockets, and the price is continuing to drop as new rockets come online. And because of that, we have these new satellites that are flying that are taking entirely new images of our planet, completely different vantage points. This is the same fire, the Kincaid fire, taken from a low Earth orbiting constellation. And you can see the difference. In fact, I'll put them side by side here to make it easier. I mean, this looks like it's taken from an airplane. The satellite's flying at an oblique angle, is seeing the fire from the side. Obviously, if you're trying to fight the fire, this photo is going to help you a lot in deciding what to do and how to do it. But here's the rub. We still operate every satellite mission essentially the same way that we did with Sputnik. Every single one is single use. It becomes trash within years of being put into space. And each one's bespoke. It requires an entirely new engineering process to design it, build it, fly it, operate it. You're looking at a photo here from NASA of all the objects orbiting Earth right now that are bigger than a 10-centimeter cube. So this problem illuminates an interesting fact about what's happening in our space industry. There's over 180 organizations around the world trying to get things off of the surface of Earth, and currently only 2 ways to get anything back. Today, Earth return is very much expensive, unavailable, and required. Today, if you want to go to space and come back, you have one destination. It's the International Space Station. It costs about $120,000 per kilogram to make a round-trip flight. And most of the time, you're on the station for probably a year before you can get that return flight home. And if we look forward to the future of what space holds for us, a future where millions of people are living and working in space, it's clear it's not a one-way street. It's clear that Earth return is very much a part of the equation just as much as launches. In fact, I would argue that there will be a point in time where more things come from space to Earth than from Earth to space. So there's really 2 interesting problems at play here. The first is that there's a proliferation of single-use satellites that are causing space debris and waste, and the second is that there's no routine access to Earth from space. So I found in my life, in my career, that there's great power in asking different questions, and especially exploring those questions and allowing yourself to come up with new ideas and new solutions. And so we did that with Outpost. And we looked first at what was the question everybody else in the satellite industry is asking, and that question is, how do we make a cheaper and cheaper satellite, so cheap we can just throw it away after a short 5-year mission? And we asked something different. We said, what if a satellite returned to Earth after its mission? And we allowed ourselves to explore that question. And what we discovered was amazing. And I'll share some of that discovery with you right now. The first is this. A typical satellite goes for about 5 years, sometimes a little more, sometimes a little longer in space. This pie chart is the cost of a satellite broken up into its subsystems. What we found over and over again, analyzing different satellites and their cost, was that 80% of the cost of a satellite has over 20 years of mission life. So at the end of a 5-year mission, there's still 3, 4, maybe more missions left in a huge percentage of the cost of the satellite. That's a lot of money left on the table. Even more surprising, we found that there's many groups right now building what's called mega constellations. These are constellations of satellites with over 1,000 satellites in a fleet flying in orbit. And when each one of those constellations is in space and active, we're going to experience a replenishment rate of 29,000 satellites per year. That means 29,000 satellites launched and another 29,000 deorbited and removed from orbit. This is a very different world in satellite operations that we're headed towards compared to where we're at today. And when you take 29,000 and multiply it by that 80% number, you realize that there's a lot of waste that is potentially about to happen, and a lot of room for improvement, especially if we can refly these satellites, if we could return them, then we could amortize the cost of a satellite over multiple missions. So I just showed that returning satellites to Earth is both a good business idea, it's also responsible, so why isn't anyone doing it? To answer that, I need to first explain a little bit of the science behind Earth return and getting from space back to Earth. So I'll start with this. This is the ballistic coefficient. Almost anything returning from space follows a ballistic trajectory, and that's basically a measurement of the mass of the vehicle divided by its drag and its surface area, or its shape. So something that comes in very fast, like a space shuttle, has a high ballistic coefficient. It comes in so fast that it's much lower in altitude before it's subsonic. A capsule, for instance, around 250 to 280, is coming in a little bit slower, a little higher up when it's subsonic. And all of this matters because when you're re-entering from space, you're up in the top right, and you fire a rocket engine to create an initial re-entry burn. And that's never 100% perfect, so there's some sort of dispersion. And if it propagates all the way to the surface of Earth, and if you do nothing about that dispersion, it could be thousands of kilometers across, meaning you have no idea where you'll land in that ellipse. Now, big vehicles, a space shuttle or a big capsule, has the luxury of carrying extra propellant to fire axial thrusters on the way in, find that nominal trajectory, and get a little closer ellipse. Still requires an ocean landing, usually still could be 5 kilometers or more in radius of unknown. Now, that all comes at the expense of payload mass. And for something like a satellite, our vehicle is 200 kilograms. It's the size of a refrigerator. We don't have room for extra propellant. We need to maximize payload. So we need a different solution. So let me challenge your thinking a little bit, because what I'm about to show you, I'm sure, is going to feel a little bit weird. You're probably expecting me to show you our newfangled rocket-breathing, fire-propelled satellite that lands on Earth, or maybe a little miniature space plane. Those solutions, while fast and hot, really don't scale in size. And so to solve return of small satellite-sized vehicles, we needed a very different solution. So we looked to the past for some hints. It turns out that the Gemini program had a very different idea for returning to Earth. This was the baseline plan for Gemini. It was to use a deploying paraglider wing called a regalo, and to actually land on ground instead of at sea, and the crew would sit upright and actually control the forward motion of the vehicle and control the capsule on a runway landing. The design was ultimately dropped when it was concluded that the material advancements for the paraglider weren't ready for prime time. Now, fast forward to today. Here's Mike flying his paraglider. It's a single surface ripstop nylon fabric. The entire wing and the entire system weighs less than 2.5 kilograms. It can carry a 300 kilogram payload. It fits into a bag the size of a child's backpack, and it's entirely controllable. He's actually controlling the flight without any energy source. It's a free flight, and he's able to land on a dime. So this was the first part of our solution. We knew for returning satellites from space. We knew that if we could get a satellite to re-enter the atmosphere and slow down high enough up, we could deploy a paraglider and still find a landing site despite the dispersions that exist. And part of the reason why is the paraglider has a glide ratio of 6 to 1, sometimes 10 to 1, whereas a parachute system is about 3 to 1. So we have a much bigger glide, and we had a suspicion we could deploy much higher up than a parachute system. But we needed a way to get into the atmosphere safely. And that's where we discovered a new type of heat shield that NASA started working on in the mid-2000s called HIAD. Now, NASA loves making an acronym out of a really long word. This is one of those. HIAD is a hypersonic inflatable aerodynamic decelerator. That's a tongue twister. I just called it an inflatable heat shield. The entire thing inflates on orbit, and it protects the payload. This is, I'll talk over this, but this is a test that they just did in November Launched out of Vandenberg, that's up the road from here, orbited the planet, inflated, came in over Hawaii and landed, safe and sound in the ocean where it was picked up. Now, what's interesting about the inflatable heat shield is it has a very big surface area. And if you remember the ballistic coefficient that I just described, that's the denominator in the equation. So the larger the surface area, the lower the ballistic coefficient. This has a ballistic coefficient that is 10 times lower than a capsule. What that means is it's coming in really, really slow. It's subsonic, very high up in the atmosphere. For the one that we're working on with NASA for our flight, we'll be subsonic at transitioning at 30 kilometers and ready to open a paraglider at 20 kilometers. And that's really important because the dispersions aren't as big at that altitude. So now we're really cooking with a solution, right? We've got an inflatable heat shield. It packs in a small volume. It's got a low mass. It gets us into the atmosphere, slows us down high up. Then we deploy a paraglider. That allows us to control our flight all the way to a very known spot on the ground. It's a completely fabric-based entry, descent, and landing system. But does it work, right? So let me show you what we've been working on to prove this out. First, we built a robot that could fly a paraglider. That was step one. And then we did flight tests with it. So first, we used our flight test platform, Mike. He would take off in his paraglider, carry the robot with him, and deploy it from his lap. Very cheap way to do iterative testing. We got a lot of tests this way. Here's Mike flying with the robot and actually flying a coordinated path together. Then we did mountaintop tests where we would hand launch the robot and let it fly precision guided waypoints all the way to the ground. And then we worked our way up to what I'll show you next is a weather balloon flight test. So we wanted to see, can we get the robot to open the wing and fly successfully at 20 kilometers, where we're actually returning from space. So here's a flight we did last year. We went up to 20 kilometers where we deployed from the weather balloon. The wing opens perfect. This was a distance test. We flew it over 180 kilometers downrange. We landed on the flight path. Everything was perfect. What you'll see in a second in the trunk of the car is the weather balloon system completely destroyed from the flight. And we just picked up our vehicle ready for the next flight. And that's all thanks to the fact that it's controlled, it's flying under its own control, and able to keep itself safe. What all of these tests have amounted to is that now we've proven that we can open the wing at these altitudes for return from space, that we can fly a GPS-guided waypoint all the way down to the ground. And now today with our tests, we're hitting a 5-meter target. So we've gone from 5 kilometers or more of landing dispersion in ocean to being able to land softly on land on a very, very precise target. So now we're building the satellite. Now we want to get actually in space to do it. So the way that works is we've developed and starting to design this vehicle. We call it a ferry. It's designed to essentially carry a payload to space, ferry the payload up, and also bring it back. We bring the customer into space, we operate them, then we inflate the heat shield, come in, open the paraglider, land, take the payload off, and eventually get good at refurbishment and then repeat the process. What we found is that the groups who want to use this today, they want it because they need a faster iteration cycle than what the space station offers, and obviously they'd like lower cost. What's really interesting with this solution, because our entire entry system is fabric and lightweight and low mass, is we can dedicate a huge amount of our vehicle to the customer's payload. A typical capsule returning from space has a 5%, maybe 10% payload mass fraction. We're in the 50% and higher range. So this is huge because what that means is the cost per kilogram to do Earth return can drop significantly and allow much more of the market to be able to access this new innovation. So where's this all going for us? Well, we understand that the mega constellations are a goal of many companies, and we really get why. It's important. So our vision is that the ferry is able to provide a replenishment service for these mega constellations where we bring a satellite up, we deploy it into the constellation, and in the same flight, pick up one that needed to be decommissioned and bring it home. And by doing both missions in the same flight, we're able to help maintain those constellations, but also not have a lot of satellites get deorbited and burn up in the atmosphere. Instead, bring them back and let all the manufacturers take part in that 80% number of that satellite has many more missions in it. So we're working on this plan. This is our roadmap to gradually build out our fleet. Every time we fly our initial missions, we'll build a new vehicle to build a bigger and bigger fleet. 5 to 6 years from now, we'll have somewhere between 50 and 100 flights under our belt, meaning we'll have a fleet of close to 100 satellite ferries ready to do these new types of missions. Our work caught the attention of NASA and Space Force in the last year. They're funding the development of this ferry system to return cargo from ISS, which is really interesting, a really interesting challenge, and also to move cargo into orbit and out of orbit. So we're using these contracts to push towards our first Earth return mission sometime next year. So I come back to this idea of the exoskeleton. If the job of an exoskeleton is to protect an otherwise vulnerable being, then I would argue that our activities in space are really doing just that, and at a very important moment. I think a lot about this. The world is becoming increasingly automated. We are constantly hearing a lot about that here at this conference. And what's typically called the industrial revolutions, I really see as paradigms in automation. The first paradigm was mechanical production. It gave way to a more automated factory, a more automated way of making things. And then 100 years goes by, and the assembly line and electrical power automate the factory even more. And yet another 100 years, and program production and computers give way to a even more automated way of making things. And now, today, we're kind of in this fourth paradigm of near perfect automation, right? There's AI and the cloud-connected factories are revolutionizing the way things are made. But there are other paradigms in the Industrial Revolution that are less focused on, less talked about. And one of which is the paradigm of location, where things are made. And this, too, is changing. Of course, we're watching more onshoring of manufacturing. Advent of 3D printers is decentralizing manufacturing in many ways. But there's another side to our technological growth, because Earth is still currently our only real location for industry to exist. And it's guaranteed that one day we will run out of mountains to turn into holes in the ground. And this is why our activities in space are so crucial. It's the promise of space development. The promise of space development is the decoupling of our technological growth from the resource dependency of planet Earth. And every single person who's gone to space and come back, many of whom are here in the audience, have come back with the same story. It wasn't the stars that caught their attention. It was the absolutely thinness of our atmosphere. And I've met many astronauts who have gone to spend the rest of their life sharing this story and trying to find ways to protect our planet. So it is my firm belief that space can be a gateway to a more resilient Earth. But we need to make our presence in space a sustainable one. To borrow from Amazon, I would say that this is still day one for space exploration. And the decades ahead are sure to be some of the most exciting times to be alive. For Outpost, we're going to start by making satellite missions that return to Earth, not only because it's a good business idea, but because it's the right thing to do. And perhaps this will be just one small step for a little space company, but hopefully this can lead to a giant leap in protecting the most important thing we've got, Earth. Thank you.